And so now we're just going to solve, the x1 by itself. We're going to solve the y1 by itself. So let's kind of go down the line here. Let's actually start with y, because I think y is probably a little bit easier. So I'm going to rewrite this. I'm going to solve for the derivative. And it equals negative k squared y. Okay. So all I've done is just rearrange this a little bit. And so normally, if we were trying to solve a differential equation, there's all kinds of techniques. If you guys have taken differential equations yet, you might learn some of these. But this particular differential equation is one of the most straightforward, in that what this is telling you is I have a function, y, and when I take its derivative twice, I get back to the same function with some constants out front. So let's think about what functions, when I take its derivative twice, do I get the same thing back? So I take one derivative, and then I take another derivative, I get back to the same thing where I started, maybe with some extra stuff. But in this case, one derivative, two derivatives gets me back where I started.
That's sine or cosine?
Sine and cosine, right? What else does that?
A combination.
So a combination of those will definitely work. There's one more function that does this.
E.
E, excellent. Exponentials. So sines and cosines do that. You take two derivatives and you get back to where you started. And exponentials do that. So if we look at our x equation, I have a second derivative with respect to x equals k squared with an x. So we have these options. We have sines and cosines, and we have exponentials. One of these is going to be exponential, and the other one is going to be sine and cosine. Which one do you think is going to be sine and cosine? Why might one of them be one versus the other? So there's kind of two ways to look at it. Let's think about just these sines, cosines, and exponentials, right? When I take the derivative of cosine, I get sine. And then when I take the derivative of sine, I get negative cosine, right? So whenever I take a derivative of sine and cosine, I get an extra minus sign, right? And so that sort of implies that the sine and cosine are going to go here, because the minus sign is already here in my equation, right? When I take a derivative of exponential, like if I take the derivative of e to the x, I get e to the x, and then I get e to the x again. So there's no negative sign there. So I'm going to have exponentials over here, and then I'm going to have sines and cosines on the y direction. However, you can also think of this by looking at our boundary conditions. So let's come back up here to our boundary conditions. If I look at my boundary conditions in the y direction, at y equals 0, the potential is 0. At y equals a, the potential is 0. So it started at 0, it's going to do something else, and then it's going to come back to 0. So in the y direction, the potential sort of repeats from one to the other. Whereas in the x direction, that's sort of the green strip that goes off to infinity. The green strip starts at a constant, v naught, and then it goes off to 0 as it goes on to infinity, right? So kind of the y direction, the blue stuff, is sort of repeating, which is kind of like a sine and a cosine. Whereas the green strip in the x direction, that's sort of starting at a value and then going off to infinity or going to 0, right? So that's a sort of a different way that you can think about that. And in fact, if I took this entire problem and just rotated it this way, I could do the exact same thing, except when I picked my made-up constant, I could have just threw a minus sign in there because my constant's made up, so I can make up the minus sign too if I want. So you always want to look at the boundary conditions to kind of decide how you separate this out. What gets the sines and cosines and what gets the exponentials. Okay, so let's apply this. So as we said, there's a bunch of functions that do this. And so for the y function, I don't even really have to do any math. I know that sine works and I know that cosine works. And so when I plug this in, my total solution is going to include both. Same thing with exponentials over here. I'm actually going to have two of them. I'm going to have an e to the kx and a b e to the negative kx. So I have a positive exponential and a negative exponential. I need both because positive exponentials do one thing and negative exponentials do the opposite. So I have to take care of both of those. The a and the b are arbitrary constants, just like the constants when you integrate and you have to add a plus c. So that's what this a and b is. I don't know what a and b are, but I'm going to figure them out. Same thing over here. I have a sine and a cosine, and so I have c sine ky plus d cosine ky. And so take a second to look at that and convince yourself that if I took two derivatives of this x function, I would get the same thing back, but with a k squared out front. Same thing for the y. If I took two derivatives of y, I would get the same thing back, but I would have a negative k squared out front. So these two functions are the solutions to these new ordinary differential equations that we've come up with. Okay, and so now all that's left to do is apply the boundary conditions to determine A, B, C, D, and whatever's going on with K. Okay? So we're going to look at the boundary conditions and see what we come up with. So if we come back to our boundary conditions, we're just going to kind of walk through them one at a time and see which ones we can apply to figure out some answers. So I'm going to start with boundary condition 1. So boundary condition 1, we said up above there is that v at x comma 0 has to be 0, right? And so this only has to do with y. So another way to say this would be sort of y of 0 is 0. And so this is just like, if you remember on Monday, we just kind of, if I know a value, I just plug it in and then use that to solve. So I'm going to plug 0 into my y of y equation. And that's c times sine of 0 plus d times cosine of 0. Sine of 0 is 0, but cosine of 0 is 1. And so what I get is c times 0 plus d times 1. And what we're told is that this has to equal 0. The boundary condition says that that must be 0. And so what that tells me is this goes away. This tells me that d is 0. So using the boundary condition, we sort of got one of our arbitrary constants. Okay. I'm gonna skip ahead to so we have boundary condition 1. I'm gonna skip ahead to boundary condition 4 for a second, because this one turns out to be pretty straightforward as well. So this is the boundary condition that says as x goes to infinity, doesn't matter what y is doing, our potential has to be 0, right? So any kind of boundary condition where you have something 0, that always sort of makes things pretty straightforward. And so this is the same as saying capital X as x goes to infinity is 0. And so I can kind of plug this in. Don't tell the math department I'm using infinity like a number. So I get a e to the k infinity plus b e to the e to the minus k infinity, right? Yeah, it should be a limit and all that, but you know, who's going to stop me? And so, according to our boundary condition, this has to equal 0, right? Well, e to the negative infinity, that's going to drop down. That's going to go off to 0. That's not an issue, right? So this guy goes to 0. We don't have to worry about that. But this, that's a problem, right? E to the, doesn't matter what k is, e to the infinity, that's going to get really, really big. But we don't want it to be really, really big. We want it to be 0. And so the only way that we can prevent that from happening is if a is 0. Okay. Questions about these first two? Excellent.